The second part of CPU virtualization, which is common to both full and para-virtualized environments, is being able to deliver events to the parent guest operating system. And these events are events that are generated by a process that belongs to the guest operating system currently executing on the CPU. Let's see what is happening to this process when it is executing on the CPU. Once this process has been scheduled on the CPU, during its normal program execution, everything should be happening at hardware speeds. What does that mean? Well, the process is going to generate virtual addresses that has to be translated to machine page addresses. And we talked at length about how the hypervisor can ensure that the virtual address translation to the machine page address can be done at hardware speeds by clever tricks in the hypervisor and or the guest operating system. In a fully virtualized environment, the hypervisor is responsible for ensuring that the virtual address gets translated directly to the machine address without the intervention of the guest operating system. And in a para-virtualized environment, once again, with cooperation between the guest and the hypervisor, we can ensure that the page table that is used for translating virtual address to physical address is something that has been installed on behalf of the guest operating system by the hypervisor so that the translation can happen at hardware speeds. And this is the most crucial part of ensuring good performance for the currently executing process in a virtualized environment. How address translations are dealt with. That's why I kept harping on the fact that virtual memory, managing the virtual memory, is the thorny issue in virtualized setting. So we know that this is in good hands. We know how to handle that. Let's look at other things that can happen to this process during the course of its execution. One thing that this process may do is execute a system call. For instance, it might want to open a file, and that's really a call into the guest operating system. That's something that this process may do. Another thing that can happen to this process is that it can incur a page fault. Not all of the virtual address space of the process is going to be in the machine memory, and therefore, if some virtual page cannot be translated, then it's going to result in a page fault. Or the process may throw an exception. For instance, it might do something silly like divide by 0, which can result in an exception. And lastly, due to no fault of this process, there could be an external interrupt when this process is executing. So these are the kind of discontinuities. These are called program discontinuities that is affecting the normal execution of this process. And the first three things that I mentioned, syscall, page fault, and exceptions, are due to this process in some shape or form. But the fourth one, the external interrupt, is something that is happening asynchronously and unbeknownst to what this process intended to do while running on the processor. And all of these discontinuities have to be passed up by the hypervisor to the guest operating system. So the common issue to both full and para-virtualized environment is that all such program discontinuities for the currently running process have to be passed up to the parent guest operating system by the hypervisor. Whether it is a para-virtualized or a fully virtualized operating system, nothing special needs to be done in the guest operating system for fielding these events from the hypervisor, because all of these events are going to be packaged as software interrupts by the hypervisor and delivered to the guest operating system. Any operating system knows how to handle interrupts. So all that the hypervisor has to do is to package these events as software interrupts and pass it up to the guest operating system. There are some quirks of the architecture that may get in the way, and the hypervisor may have to deal with that. Recall that syscalls and page faults and exceptions are all things that need to be handled by the guest operating system. So it probably has entry points in it for dealing with all these kinds of program discontinuities. Now, some of the things that the guest operating system may have to do to deal with these program discontinuities may require the guest operating system to have privileged access to the CPU. That is, certain instructions of the processor can only be executed in the kernel mode, the privileged mode. But recall that the guest operating system itself is not running in a privileged mode. It is above the red line, which means it has no more privilege than a normal user level process. This is a problem especially in a fully virtualized environment, because the fully virtualized environment, the guest operating system has no knowledge that it does not have the privileges. So when it tries to execute some instruction that can be executed only in privileged mode, the expectation is that it'll trap, get into the hypervisor, and the hypervisor will then do the work that the fully virtualized guest operating system was intending to do. But here is where the quirks of the architecture come into play, because unfortunately, some privileged instructions fail silently in some architectures when they are executed at the user level. And this is a problem for the fully virtualized environment where the binary is unchanged. In the para-virtualized environment, because we know that the para-virtualized guest is not running on bare metal, we know that it does not have the same privilege as the hypervisor, and therefore we can collaboratively make sure that anything that the guest has to do in privileged mode, it can take the help of the hypervisor to do it. But in a fully virtualized setting, the guest has no knowledge. So the only mechanism that will save the day is if the guest tries to execute a privileged instruction, it'll trap into the hypervisor, and the hypervisor can do the necessary thing. However, because some instructions, when executed in the user level, even though they are privileged instructions, they don't trap but fail silently, and that can be a problem. This happens in older versions of x86 architecture for privileged instructions executed in user mode. Therefore, the hypervisor has to be intimately aware of the quirks of the hardware and ensure that there is workaround such quirks. Specifically, in a fully virtualized setting, the hypervisor has to look at the unchanged binary of the operating system and look for places where these quirks may surface and do binary rewriting in order to catch those instructions when and if they are executed on the CPU. Having said that, I should mention that newer versions of Intel's architecture and AMD architecture for the x86 instructions have included virtualization support so that these kinds of problems don't occur. As a result of servicing the events that are delivered by the hypervisor, the guest may have to do certain things which may result in communication back to the hypervisor. In the case of a fully virtualized environment, communication from the guest to the hypervisor is always implicit via traps. For example, as a result of page fault servicing, the guest may try to install a new entry into the page table. When it tries to do that, that's a trap that will come into the hypervisor, and the hypervisor will take the appropriate action. In a para-virtualized environment, the communication from the guest to the hypervisor is explicit. So there are APIs that the hypervisor supports for the guest OS to communicate back to the hypervisor. What may be reasons for that? Well, we talked about memory management done by the guest operating system in a para-virtualized environment, such as Zen, where the guest operating system may have to tell the hypervisor, here is a page table entry, please install it in the page table for me. So that is the kind of communication that may have to come back from the guest operating system down to the hypervisor.